Hello there, random smart person on the internet. Did you know that there is an energy field created by all living things? It surrounds us and penetrates us and it binds the galaxy together. That's right, I'm talking about the force of gravity. Gravity is a fundamental force of nature that causes objects with masses to be attracted to each other. It is one of the four fundamental forces of the universe, along with electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity is responsible for many phenomena that we observe in the universe, from falling objects on Earth, to the orbits of planets around the sun, and to the formation of galaxies. Gravity can be thought of in two ways: Newton's theory of gravity and Einstein's general theory of relativity. All the way back in 1665, Isaac Newton observed an apple falling from a tree. This made him think about motion. He hypothesized that the same force that pulls the apple to the ground also pulls the moon towards the Earth. This force is called gravity, and it attracts all objects towards each other. The strength of gravity depends on the masses of the objects and the distances between them. Newton figured out that the Earth keeps pulling on the moon towards it with gravity. At the same time, the moon keeps moving ahead of it with inertia. Earth curves away from the moon as it falls towards it, so the moon winds up in orbit around the Earth. In the same way, the planets are in orbit around the sun because of the sun's gravity pulls on them while their inertia keeps them moving ahead. Therefore, the planets are moving around the sun and end up in an orbit. In your everyday life, you experience gravity the way Sir Isaac Newton explained gravity. Students today learn Newton's law of universal gravitation in science class. Or should be learned by kids today. Have you seen people interviewed on the street online and they don't know this basic knowledge? Kids, pay attention in school and listen to your teachers so you don't look like fools on the TikTok or the Instagram or the YouTubes or whatever the newest app is you whippersnappers are using. Back in my day, it was MySpace, and the kids today won't know the difficulty of choosing your top 8. Cool it, Grandpa. In 1687, Newton published his law of universal gravitation, which looks like this, where F represents the gravitational force between two objects. G is the gravitational constant, which is approximately 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared. M sub 1 and M sub 2 are the masses of two objects, and R is the distance between the centers of the two objects. There are two key points that you need to know in order to understand this equation. First is the inverse square law. It means that if you double the distance, R, the gravitational force, F, becomes 4 times weaker. If you triple the distance, the force becomes 9 times weaker, and so on. This explains why the force of gravity weakens as the object moves further apart. Second is that gravity is directly proportional to the masses of the two objects involved, in this case, M sub 1 and N sub 2. This means that the larger the masses, the stronger the gravitational force is between them. For example, the Earth's mass is much greater than the person's mass standing next to you, and therefore exerts a force on you much stronger than the person next to you. Although the person standing next to you is exerting a non-zero force on you, it's so small that in our everyday lives we just say it's zero. Gravity affects everything from people to planets to stars and to black holes. Unlike other forces such as the electromagnetic force, gravity is always attractive and never repulsive. It is a continuous force that acts over any distance, although its strength diminishes with distance. Gravity plays a crucial role in the formation and the dynamics of galaxies, stars, and other structures in the universe. It is responsible for holding galaxies together and determining their shape. On Earth, gravity imparts an acceleration of approximately 9.8 meters per second squared to all objects near its surface. This is often referred to as the acceleration due to gravity. Newton's law of universal gravitation revolutionized the way we understand the universe. Before Newton, another astronomer and mathematician, Johannes Kepler, established the laws of planetary motion, describing how planets move around the sun. But they didn't explain why. Newton's theory showed that Kepler's laws could be derived from the laws of universal gravitation, providing a deeper understanding to the celestial mechanics. Newton's laws accurately predicted the orbits of almost all of the planets in our solar system, confirming its validity and helping us understand how planets move. And this makes sense. Take a ball and drop it straight down, with no forward force. The ball will drop straight to the ground. Toss the ball a little forward, and it may go a few yards, but ultimately it will hit the ground. Now throw it as hard as you can, and you may even get the ball to travel a few dozen yards. Now what happens if you shoot this ball out of a really big cannon? It will go really far before falling back to Earth. But what if we got it going so fast that as it was falling towards the Earth's curvature was falling away from the ball? Yes, the Earth is curved because it's an oblate spheroid and not flat. I can't believe I have to say this in a science video. This is the same principle as our satellites or our International Space Station. The International Space Station is traveling around Earth really fast. 17,500 miles per hour fast. Fast. It is always falling back to Earth due to Earth's gravitational pull. But since it is going so fast, it keeps missing Earth and stays in orbit. This exact scenario is Newton's first law of motion in action. When negating for air resistance, objects in orbit will stay in orbit forever. However, because near Earth, space is not a perfect vacuum, eventually the satellites that are orbiting it in low Earth orbit will slow down enough to fall back to Earth. This is why every so often, some satellites need to use some of its fuel to keep in a stable orbit and counteract the effects of the atmosphere. Physics students know what I'm talking about whenever I say negating for air resistance. Newton's law is still used today for space exploration. It has a profound impact on our understanding of planetary motion, space exploration, and everyday experiences on Earth. It helps us calculate trajectories of spacecraft, ensuring that they reach their destinations accurately. We used them for Apollo to first go to the moon in the 1960s and 1970s, and we're still using them today for Artemis to get us back to the moon soon. Nearly 400 years later, Newton's law is still relevant. However, Newton's theory of gravity isn't the only game in town. A very smart person named Albert Einstein, you may have heard of him, published his general theory of relativity in 1915. This provided a new understanding of gravity. Instead of describing gravity as a force, Einstein proposed that massive objects curve the fabric of space-time itself. The core principle of this theory is space-time curvature, which is the idea that massive objects, like planets and stars, actually warp the fabric of space-time in their vicinity. Einstein merged space and time into a single unified entity called space-time. This fusion of dimensions allows us to describe the four-dimensional fabric of the universe. According to Einstein, massive objects cause space-time to curve around them. Imagine placing a heavy ball in a rubber sheet. It creates a depression, causing nearby objects to move towards it. Similarly, massive objects create a gravity well in space-time, and other objects move along curved paths in response. This concept challenges the traditional view of gravity as a force and instead treats it as the consequences of space-time curvature. While we can test Newton's view of gravity, could Einstein's theory be tested that masses curve space-time? Yes. One of the most celebrated predictions of general relativity is that massive objects can bend the path of light. To test this prediction of light bending made by general relativity, a British astronomer, Sir Arthur Eddington, organized an ambitious scientific exploration during the total solar eclipse of May 29, 1919. The eclipse offered a unique opportunity to observe the positions of stars close to the sun in the daytime sky, where they would normally be obscured by the sun's intense brightness. Two teams, one in Brazil and the other on an island off the west coast of Africa, conducted simultaneous observations during the eclipse. They aimed to measure the apparent shift of the positions of stars near the sun during the eclipse, compared to the positions when the sun was not in the vicinity. The results of these observations were groundbreaking. They revealed that the positions of the stars near the sun were indeed shifted, as predicted by Einstein's theory of light bending due to gravity. The amount of the bending observed during the 1919 eclipse was approximately 1.75 arcseconds, which closely matched the predictions of general relativity. 1 arcsecond is 1/3600th of a degree. That's really small. The confirmation of Einstein's general theory of relativity during the solar eclipse was a monumental achievement with profound implications. It provided strong experimental evidence in favor of general relativity and solidified its status as a groundbreaking theory of gravitation. General relativity revolutionized our understanding of gravity by replacing the classical concept of gravity as a force with the idea that gravity results from the curvature of space-time. The success from this experiment opened the door to a new era of astrophysics and cosmology, allowing scientists to investigate the behavior of light and matter in the presence of massive objects like stars and black holes. This singular eclipse catapulted Einstein to international fame, turning him into a scientific celebrity and a symbol of the power of human intellect. This stands as a defining moment in the history of science, where the elegant predictions of Einstein's general theory of relativity were confirmed through meticulous observations. This pivotal event reshaped our understanding of gravity and forever altered the landscape of theoretical physics and astrophysics. Einstein's theory of gravitation, with its profound insight into the nature of the universe, continues to be a cornerstone of modern physics and a testament to the power and experimental verification in science inquiry. So which one should we use? Newton's law of gravitation or Einstein's general theory of relativity? Well, both. We can use Newton's law of gravitation for 99.99% of everyday physics and astronomy. But there is still that 0.01% where Newton's laws break down and we need to use Einstein's general theory of relativity to arrive at the correct answer. Or 0.01% for our friends across the pond. One of these places that Newton's law doesn't work is in strong gravitational fields. For example, Remember at the beginning of the video where I said Newton's laws accurately predicted the orbits of almost all the planets in the solar system? It correctly predicted the orbits of 7 of the 8 planets. Sorry, Pluto. Hashtag Pluto's not a planet. While Newton's law correctly predicted the orbits of Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, it failed to accurately predict Mercury's orbit. Astronomers at the time attributed Mercury's peculiar orbit to an unseen planet between the Sun and Mercury called Vulcan. Many astronomers attempted to locate the planet but were unsuccessful because it wasn't there. It wasn't until Einstein came along with his general theory of relativity that astronomers can solve this mystery. When you plug in all of the information into Einstein's equations, Mercury perfectly follows the predictions laid out by Einstein's theory. And while Einstein's theory is able to explain everything that Newton's laws can, there's a small area of the universe that we know it breaks down and does not work. Einstein's theory of general relativity does not work at the atomic and subatomic scales. This is where quantum mechanics comes into play. Quantum mechanics explains what happens at the atomic and subatomic scales, while general relativity explains what happens at the macroscopic scale. Relativity is correct when applied to the macro scale, and quantum mechanics is correct when applied to the micro scale. But relativity is wrong when applied to the micro scale, and quantum mechanics is wrong when applied to the macro scale. This is where the science of quantum gravity comes into play, which has not been solved yet. If you want to be guaranteed a Nobel Prize, millions of dollars, international fame, and live on forever in history like Newton and Einstein, study hard and solve quantum gravity. It would be cool if this video inspired a person to become a scientist so that he or she could solve quantum gravity. And just remember me and cut me into like 5-10% of your winnings. You can send it my way. So there you have it. You learned about the different ways Newton and Einstein use science to explain gravity. Leave a comment down below on which is your favorite scientific law and theory and why. Comments are good for the YouTube algorithm. If you would like to learn more about how gravity is being used to assist the European Space Agency's probe JUICE to travel to Jupiter, click on the video right here. Or, if you would like to learn how Hubble and the JWST are being used to explore Jupiter's moon, Io, click on the video right here. And always remember, have fun with STEM.